Thank you, Jody. That was very inspiring. Let me ask our plenary speakers maybe to come forward. So the format for our next session here is a plenary panel of three scientists discussing emerging science in riparian ecology and management. And so we are trying to go for a sort of broad range of topics and sort of exciting new fields in understanding how riparian systems work and approaches to conservation and restoration. So what we'll do is we'll have three 20-minute talks, and if you can hold your questions, we'll have a half-hour discussion, sort of roundtable discussion afterwards. So our first speaker, it's my pleasure to introduce Mike Scott. Mike is an ecologist who has essentially written the book on cottonwood and dominated ecosystems, has worked for 25 years as a research ecologist for the USGS, currently is emeritus and adjunct professor at Utah State University, and is doing exciting work looking at historical ecology and historical changes in the Grand Canyon using using photographs, historical photographs and current ones. He's also working on invasion of riparian zones on the Escalante River, has worked in the past on Great Plains rivers, and has understood and given us a better understanding about how these western cottonwood-dominated ecosystems work. So I'll give a hand to Mike, and he'll be our first speaker.
Thanks, John, and it's a real pleasure to be here. And I want to thank Jody for a very inspiring and exciting and inspirational talk. And I want to continue with Jody's theme, but I want to sort of come down out of the mountains a little bit and shift the focus to riparian vegetation, and then share with you some insights from work that colleagues and I have done on riparian systems, primarily on the Missouri River and the Colorado River, and actually talk about some more heavily impacted riparian landscapes. And it's really, I think, through some of those pathologies that we are able to learn and understand better how these systems respond to disturbances, and hopefully with that better manage and restore some of what has been lost with these systems. All right, well, again, sort of connecting with Jody's theme, I want to point out that riparian ecosystems dominated by cottonwoods and willows in western North America exist from northern Canada through the U.S. into northern Mexico. This is a striking uniformity of habitat across a very large longitudinal gradient. And of course, these systems are important for a number of migratory species, including songbirds, which use these habitats on a continental scale for migratory stopovers, wintering, and breeding and nesting. The fact that these systems are so uniform in terms of their compositions owes to the fact that these systems are structured and maintained by high flow variability, which feature relatively frequent large flood events. So let me just quickly shift to the Missouri, which I'll sort of weave, the Missouri River, which I'll kind of weave throughout my talk here. The Missouri River is the longest river in the continental U.S. and is an example of a once continuous riparian corridor which has been heavily fragmented by dams, which show up here as orange bars, which then leave behind isolated segments, remnant segments of free-flowing river, separated by large reservoirs, which are indicated in dark blue. The lower third of the Missouri River has been converted to basically a shipping canal for barges. Well, cumulatively, these impacts have endangered a number of species, including the pallid sturgeon, which migrated long distances as part of its life cycle, similar to Pacific salmon. And as well, the reservoirs have inundated thousands of acres of bottomland riparian cottonwood forest. Well, I've talked about the fragmentation that results from dams. And whereas dams have provided tangible benefits to human communities, they've also set off a very slow reveal of physical and biological impacts, some of which we're still only beginning to understand because of their complexity and the long timescales involved in the playing out of these changes. So I'll just, in the time remaining, I'll talk a little bit about hydrologic impacts from dams and some of the second-order impacts, both biological and physical, that result from that, and what we've learned from those, and then going forward, perhaps what we might be able to do from a restoration perspective, and then how newly emerging technologies and approaches, which Hervé and Tom will be talking about after me, might be used in improving restoration outcomes. All right, well, let me first start with flow regulation, which is really kind of a primary driver of ecological decline of riparian ecosystems. And the effects of large dams is illustrated in this hydrograph of the Missouri River at Bismarck, North Dakota. You can see, following the completion of large dams on the Missouri, the once relatively frequent large snowmelt peak flows have been virtually eliminated, and low flows have been increased. These have very distinct and important impacts on the riparian communities. And only in 2012, almost 60 years after the dams went in, did we have a flood that was comparable of historical magnitude, but not duration, to the historical flood flows, leaving open the possibility to examine if restoration of floods on a dammed river might be able to be used to at least restore some of the ecological processes that have been lost as a result of the dams and were legacies of the pre-regulation river. We talk also about change, very quickly, about change in channel form and function. And a very common channel response to damming is channel narrowing and channel simplification, which has tremendous impacts and implications for aquatic ecosystems. Channel narrowing typically involves the encroachment of riparian or upland vegetation onto formerly active channel surfaces. And let me illustrate the changes that occur over time as a result of damming using an 1890 photo here from the Grand Canyon, the Colorado River in Grand Canyon below Glen Canyon Dam. You can see in 1890 there was a very large a very wide, largely unvegetated active channel. Very frequent large floods would come down and rework the river channel in the canyon. And aside from just a few little patches of vegetation and fine textured eddy deposits, there was a distinctive band of vegetation characteristic species that would occur at the average high water line of these old floods. So you can see how big these floods were in the Grand Canyon prior to damming. Well, the channel narrowing can be seen in this 100 years later in a photo taken from the same location. And you can see that below the old high water line of vegetation now, large stands of dense tamarisk have established, in addition to a number of other native high waterline species. And this old eddy deposit now is filled with sand and dominated by desert grasses. Well, in response to continued decreases in peak flows and increases in low flows as a result of change in dam operations, by 2010, encroachment has intensified. And this, in Grand Canyon particularly, this sort of illustrates the sort of complexities from a management perspective that we get into with these resulting changes. Because on the one hand, because this vegetation has sort of increased the diversity of birds in Grand Canyon, that's kind of a good thing. On the other hand, the native tamarisk, the non-native invasive tamarisk, are also preferred nesting sites because there are so few nesting sites there. So the removal of tamarisk in Grand Canyon is controversial because you're messing with nesting sites. And at the same time, recreational boaters have a really hard time finding campsites because they're all covered with vegetation now. So anyway, let's move on quickly to successional processes, which again in riparian systems were driven by flood-caused erosion and deposition. And let me use an example from the Missouri River. Pioneer species would colonize freshly deposited river sediments and succeed to progressively more complex secondary forests. But at any stage, any of these forest assemblages could be recycled by floods back into river deposits, which would again begin the cycle. But as a result of flow control now, this cycle has largely, this recycling portion of this successional cycle has been severed, sending these existing forest communities off into successional trajectories that are as yet unknown. Some of the changes have been well predicted, but some of the changes have been rather surprising and not in a particularly good way. One of the predicted changes that we did see come to pass was the obvious decrease in the early successional cottonwood community. You can see in 1970 there were large numbers of relatively young, small diameter cottonwood stems. But 40 years later, those stems have gotten larger, older, but have largely failed to reproduce themselves on the flow-controlled river. One of the changes that was not well anticipated was the relatively dramatic increase in the in both woody and herbaceous invasive species. For example, smooth brome, which is a invasive species in western North American prairie grasslands, has made a dramatic inroad into these forest stands, dominating virtually all of them 40 years later and threatening the biodiversity of these forest understories. Well, regulated rivers aren't the only places that invasive species are establishing, as evidenced by this picture of Canyon de Chelly in Arizona, showing a massive invasion of Russian olive. And a sampling of over 500 streams from across 17 western states has shown that Russian olive is now the fourth most abundant woody riparian species behind native sandbar willow, cottonwood, and tamarisk. Although Russian olive existed in the drainage, in the watershed of Canyon de Chelly as early as the 1930s, it wasn't until 1980 that the invasion exploded, coincident with a shift from a regional wet period to a regional dry period, suggesting that there was a climate connection to some of these invasions. Well, it was long hoped that, that restoring flood pulses, even on regulated rivers, could reset or at least reinvigorate some of the ecological processes that had been largely lost as a result of flow regulation. And whereas there has been some demonstrated success on smaller streams by using this approach, results from the follow-up studies on the 2011 flood on the Missouri River suggest a little bit different story, and that is, even though there were transitory increases in sandbar areas, which was a good thing, there was little channel migration, which was somewhat unexpected and disappointing, in addition to the loss of the very few young cottonwood stands that had established in the post-dam era. And surprisingly, very little cottonwood recruitment in flood and subsequent years, leading some authors to suggest that the river had entered a new geomorphological and ecological stable state. So you could look at a stable state as perhaps this ball and cup illustration, where the ecosystem kind of stays within this cup in response to minor perturbations. But ecosystem ecologists suggest that a perturbation to an ecological driver, say that is the imposition of a dam, if that causes the system to enter a new stable state, then the removal of that perturbation is not likely to return the system to initial conditions. Now, demonstrating stable states with large complex ecosystems is a very difficult thing to do. And the Missouri River system, for example, is still showing directional change. Nonetheless, this is a sort of a useful heuristic tool in anticipating the future. For example, if the Missouri River, which is now in a degraded state, having lost some level of complexity and function, through time has a number of potential states or fates available to it. If it's in a stable state, it might remain the same. It might continue to decline. Or with human intervention, there are a number of possible, or there's a family of possible restoration states. To me, understanding and predicting better the restoration futures of riparian ecosystems is an exciting new research frontier. All right, well, lest you think I'm a complete pessimist about the fate of riparian ecosystems, let me just point out a few potential bright spots. Reservoir deltas are forming on the Missouri River, and these deltas represent an area more than twice that of the existing forest area in remnant reaches. And a number of these deltas have a relatively large aerial extent of early successional cottonwood forests on them. And of course, as Jody alluded to, dam removal is sort of an exciting prospect, like the Elwha Dam. And in the sense that you're basically removing those primary drivers of ecosystem decline. However, assuming the system has not entered a new stable state, it may be decades before we fully understand the degree to which the system has returned to initial conditions. All right, number of issues and challenges facing us. And one is basically the large uncertainties associated with some of the pyramid of changes that occur over relatively long periods of time. Although we understand fragmentation, loss of flow variability fairly well now, still large uncertainties associated with successional trajectories, state changes, invasive species, invasion processes, the effects of invasive species on existing systems, and what potentially are the effects of climate warming. Process-based restoration, like prescribed flooding, faces a number of challenges, both operational and structurally. And in the case of the Missouri River Basin, for example, management conflicts limit large-scale restoration options primarily because of the existence of multiple stakeholders with divergent goals, and again, especially in the case of the Missouri River Basin, regressive anti-government politics. Again, some bright spots: dam removal, novel habitats like delta reservoirs. But again, new technologies and modeling approaches like those that Hervé and Tom will be talking about are desperately needed, particularly with regards to predicting restoration futures. Thank you. Thank you.